Today we're going to talk about a topic called continuity and another called end behavior. So the general definition of continuity is a function that has no breaks. In other words, you can draw it without lifting up your pencil. So rather than talking about types of continuity, which most graphs have, let's talk about the types of functions that don't have continuity, or the types of discontinuity. We have infinite discontinuity, which means a graph that has something like an asymptote in it. So if you remember from last year, we had graphs that looked something like this, had an asymptote, and then did something like this. All right, that would be an example of an infinite discontinuity. Jump discontinuity is usually called like a piecewise function. For instance, if I have something like so, that's jump discontinuous because you draw it by holding your pencil down and then you have to jump up to get to the next piece of the graph. This one you also have to jump, but you jump over an asymptote. Point or removable continuity. This is a situation where you have a graph doing whatever it's doing, and then there's one point where that graph ceases to follow its original pattern. And in order to get to another point, granted you jump, but it's a singular point, whereas a jump typically does not continue along the same path. This is a graph of a parabola, except for this point that's removed here. So those are three types of discontinuities. Let's take a look at these actual graphs. Now we want to know if they are continuous or discontinuous. Well, we don't even have to graph these to figure that out. We could, and it would make life a lot easier, but we know something about these functions anyways. This is a cubed function. We know pretty much all cube functions look like this. So, and I can draw that without lifting up my pencil. So this is continuous. Now, this function, we may not know how to graph this at this point. However, we do know that in the denominator, there are two places where x cannot have specific values. The domain is restricted, we say, at -5 and at 1. Now, when that domain is restricted, that means typically you create an asymptote. And we'll talk about this a little bit more later. But at -5 and a +1, these have asymptotes. So we know it's not continuous. It's not asking us which type of discontinuity we have, just whether or not it's continuous. We want to know if this next function is continuous. Now, it would appear, since it's a piecewise function, you're going to say, oh yeah, this is not going to be continuous because it's going to be jump. However, let's graph it first. We need to know what it looks like, so we need to find out where the function begins and where it goes. So I take the x value, pop it in, and see what my y is. We end up with 8. Now you'll notice that in the second part of the function, the y value is also 8. So if I were to take and graph this, I go over to 1, up to 8, and this says open circle that point, and then do a slope of 3 but going to the left. So a slope of 3 going to the left looks something similar to this, where I have a y-intercept of 5. And then if I want to graph y equals 8 when x is greater than or equal to 1, you'll notice that I have to go to 1 and 8, which was an open circle, but now it's filled in. And then I go horizontally to my right. So I can actually graph this function without lifting my pencil. Thus, it's continuous, yes. So that was kind of if you got lulled to sleep, you'd assume that it's going to not be continuous, but it actually is. So kind of a trick. Now we're going to switch to describing what we call end behavior. And you should have done a little of this last year. So the premise of end behavior is it describes the y value of the function when x goes to positive or negative infinity. In other words, when x is way the heck out there and way the heck out here. All right? And we're going to state the end behavior of x to the 7th. Now, you may not know what x to the 7th looks like. I've got a pretty good idea, but you may want to take a look at your calculator to figure this out. So let's get those out. So the first thing we'll do is we'll hit the y equals button and type in the function x raised to the 7th power. Next, you'll need to set the window appropriately. I guess you could probably set it in the standard window. So go zoom and 6 standard. And we should have enough to see what's actually going on. Now, notice this function. You'll notice that in this graph, if I move to the right, the graph increases and appears to go up forever and ever. And it actually does. And if I move to the left, you'll notice the graph drops forever and ever, which it actually does. So in order to state the end behavior, we do so as follows. We say, as x goes to infinity of the positive type, we could say f of x, or for that matter, we could say y, doesn't really matter. Let's make that a little bit better. Goes to positive infinity. That's one part of describing the end behavior. Then we'd have to describe what happens as x goes to negative infinity. Well, let's take a look at the graph again. And as we move towards negative infinity on this graph, we notice the graph continues to go down. So we say f of x also goes to negative infinity. Much of the time, our answers are going to look very similar to what we have here. Let's move to the next problem. Now, state the end behavior for both of these two functions. Well, there's a trick. We can actually graph this, or we can think about what's really happening here. In order to state the end behavior, I have to say, as x goes to positive infinity, and as x goes to negative infinity, what does y do? Let me just write y in this case. Now, think about how big infinity is. It's bigger than you can ever imagine. So I want to know what happens when I take 5 times infinity cubed minus 7,000 times infinity squared minus 5,000 times infinity. Kind of tough to imagine how big that is, but think about it this way. If I take infinity and square it, that's ridiculously big, and multiply that by 7,000, that's 7,000 times bigger. But take a look at this first term. If I take infinity cubed, now think about it, that's infinity squared, which is right here, times a whole nother infinity. It's infinity times larger, which is way more than 7,000 times larger. So this first term in all of these polynomial functions is going to outrule everything else. So really, I mean, this is just here as fluff. It's garbage. It doesn't even matter. Because in order to describe the end behavior of a polynomial function, this first term, or the biggest term with the highest degree, is what's really going to matter. So as we go through, we now state that as x goes to infinity, since this is overruling everything, y must go to infinity. And now we know if we plug negative infinity in here, then a negative times a negative times a negative is a negative times 5, still a negative. This must go to negative infinity. We could graph this on our calculator and verify that if we wanted to, but really after the explanation, we shouldn't need to. So now we want to describe the end behavior of this next function. And again, we look at the degree value, which is the highest. That's the 4. And this is my only term that should ever matter. So I'm just going to say, forget looking at all these guys. And let's just look at this first term again. All right, so what we're really looking at is 8x to the 4th times negative 8. So now we say, well, as x goes to positive infinity, what does y do? Well, if I take a positive number and raise it to the 4th power, that continues to be positive, but then I'm going to multiply it by a negative 8, and I actually get a negative number. So as x goes to infinity, y goes to negative 8. That's one part of my end behavior. Then we're going to take and let x go to negative infinity and decide what y is going to do. Well, once again, if I plug a negative infinity and cube it, we get a negative, but now I'm taking it to the 4th power. So a negative multiplied by itself 4 times gets you a positive, multiplied by a negative 8, and I get a negative. So we've got, as x goes to infinity, y goes to negative infinity. In other words, the graph is going to do something like this. We don't know what's happening in the middle, but that's not what end behavior talks about. It only talks about the two ends. Whereas this graph over here said at the end of the right side, it goes like this, and at the end of the left side, it goes down. I don't know what it does in the middle. Let's move on. Next, we're going to talk about increasing and decreasing functions. So here's kind of the book's definition of an increasing or decreasing function. Basically, as you read through these, think about what this really means, okay? F of A has to be less than F of B for any A less than B. In other words, if I'm increasing, my graph has to rise. If I'm decreasing, my graph has to fall. Now, we're talking today, we're going to be talking about intervals of increasing and decreasing because we know functions do different things. For instance, a cubic function could do something like this, depending on what else is there. All right, let's take a peek. So we're going to look at the following graph. Y equals negative 3/5 x plus 8 squared plus 14. We know from our studies already that this is a parabola sliding over 8, up 14, and then since I have negative 3/5 as my y value, this is going to go down. We have a good idea of what that's going to look like. Now, we want to determine the intervals where the function increases or decreases. So we start from left to right to describe everything because that's how we read. Now you notice as you follow this from left to right, it rises. So it's actually increasing until it gets to its vertex point. And then it decreases or goes down after the vertex point. So how do we say that mathematically? We say the function increases, and we're going to do this in interval notation, starting at negative infinity until the x value of the vertex, so until right here. Now the x value of the vertex is described by the h value here, so until negative 8. Then we know the function starts dropping. Notice, when we're describing our intervals of increasing or decreasing, we're talking about x values. So this decreases from that x value of -8 forever, all the way to the right. So we call that infinity. We leave these as parentheses rather than brackets because in theory, it's neither increasing or decreasing at this point. It's kind of flat. Let's move to our next example. Now, this function, you probably don't know what it looks like. So again, we're going to move to our calculator. So you'll see I've gone to y equals and plugged in our function 5x cubed plus x squared minus x plus 4. Now, just for kicks, let's just graph this in the standard window. So that's zoom 6. And what that'll do is graph it from -10 to 10. We see this graph tends to move up. Something happens here, and then it goes up. I want to zoom in on this spot to see what particularly happens, because I'm not sure that it just slides over horizontally and goes up, or if it goes up, down, and up. So to do that, I'm going to do what's called a box zoom. I'm going to hit the zoom button, hit the number 1 for box, and you'll notice I've got a blinker right here. I'm going to take that blinker and move it close to my point of interest. And then I'm going to create a box around it by hitting enter, dragging it over, and dragging it up. I'm going to hit enter again, and what this does now is it blows up that one small part of the graph. And you'll see from the picture that this graph rises, falls, and then rises again around these 2 points. Now, if I'm going to state the interval where my function increases and decreases, I'm going to need to find these 2 points to do that. So I'm going to start setting my intervals up right away. I'm going to say this increases and decreases at the following points. Well, you'll notice that from -infinity up to this point, it rises. I just don't know what that point is. And it also rises from some point to infinity. What did I just do? Killed that. Ignore what I just said. It also rises from some point, once again, to infinity. And it's going to fall from this point up here to this point down here, but I don't know what either one of those are, so I'm just going to leave that open. And now we're going to find these 2 points of interest. This is a relative high point. We call it a maximum. So I'm going to find this relative high point. Now, what I could do is I could trace, but the problem is trace is kind of worthless because it doesn't get to the exact high point. You can kind of guesstimate it, but is it its highest right at this point of 3.48 or here? I just don't know. My calculator will do this for us. If I hit the second button and followed by the trace button, which says calculate up above, I come to this new menu. And it says, well, I want to calculate the maximum value of this curve. So I'm going to hit the number 4 for maximum. Now it asks me to find my left bound. We want to go, that means go to the left of your highest point that you're looking for. So I'm going to move my blinking guy to the left of this high point. I'm going to hit enter. Then it's going to switch to the right bound. I want to move now to the right of that high point by cursoring over. And now you'll see that I'm to the right of that high point, and I'm going to hit enter. For some reason, our calculator asks us to take a guess, which is pointless, but it does. And we'll hit enter a third time. And now what we're interested in is this X value of this high point, because that's where it stops increasing and starts decreasing. And that looks to be the point 0.333. So I'm going to say that this graph increases from negative infinity to negative 0.33. I'll throw another one in there for kicks. All right. Next, I want to find out where it starts increasing again. That's going to be here at this low point. So we're going to go back to calculate, second trace, which is really calculate. And this time we're going to find the low point, which is known as the minimum. So I'm going to hit the number 3. And again, my calculator is going to ask me to find the left bound, so I want to go left of my lowest point. I'll move this over a little more. Doesn't really matter how much as long as you're to the left. Hit enter, and then it's going to say find the right bound. So I need to go to the right of my lowest point that I'm looking for, which I've done. Hit enter. There's that dumb guess again, and I'm going to hit enter a third time, and it's going to calculate an X value of my low point, where it stops decreasing and starts increasing again. So this increases from positive 0.2 to infinity. Now you'll notice this negative 0.33 was the X value here, and 0.2 is my X value here. And that's where it decreases. So I can just fill that in. So negative 0.333 to positive 0.2 is where my graph decreases. That's all I've got for you. Answer these questions on the forum, and we'll get back to you tomorrow. Thanks.